That was just for showing up. Thanks for that. I'll try to keep you entertained in this second to last session. I'm going to talk about common security pitfalls for APIs. As you can imagine, I'm going to cover some things that you probably know about, maybe some things that you have known about but forgot. And if not, I'm going to put things into context. Before we start, let's take a look at what an API exactly means. So let's see what we're going to talk about. We have a browser application on the top. We have a server or servers on the right. And essentially what's going to happen is that we are going to load our application from one server, and then we're going to fetch data from an API. And this thing is not working. My apologies. And then we're going to fetch data from an API and work with that data. So you can imagine this kind of setup changes a few things. It has an impact on certain security properties, but it also maybe simplifies a few things. What I want to talk about is security vulnerabilities in this API. And I have no idea what's going on. When I tested this, everything was fine. Let me quickly fix that. Anyway, what I want to talk about is security problems in this API setup. Essentially, what's going to happen is that we're going to see a lot of the same vulnerabilities, but now they occur in an API context. And if you recognize this image, then you have been following the security news. And the security news, essentially, this is from the OWASP Top 10, 2007, but the first release candidate, the one that got rejected, and after which they made a new one. Nonetheless, I want to point this out because it's actually quite an important screenshot. It's a fact that we see the same vulnerabilities appearing in APIs. And I assume, and I've been reading up on this, and one of the reasons that this thing is no longer in there is because essentially a lot of the other issues are subsumed by this one. They reappear in this time in the form of an API and its security problems. So in this talk, I'm going to talk about a few pitfalls. I'm going to cover, I haven't counted them, I think it's about 10 different topics. We're going to flow through the presentation. It's going to be structured fairly logically. But by the end, you have a good idea of things to look out for, common mistakes in an API, even by people that should know better or do know better, they still make mistakes. Before we start, a small word about myself. I'm Philippe De Ryck from Leuven. I have been working in web security for a long time. I did a PhD in web security, and since then, I've been giving trainings to companies, teaching developers how to recognize security problems, how to fix them, how to build more secure applications. Two relevant things about what I did recently, or am doing. I've built an online security course for the university. It's a free online course about web security fundamentals, things that essentially every developer should know. So if you're interested in that, or you know people that should know those things, point them towards that. And I'm also co-organizing the SecOpDev course, which is a week-long course on security, not only web security, but software security in general. Seba de Ryck, who gave a training here yesterday, will teach there next year alongside about a dozen other experts from all over the world. So that's also a very interesting reference if you want to learn more and if you want to learn about all kinds of security, essentially. Now let's talk about APIs. What's the first thing that matters in an API? Come on, who can take a guess? You're contacting an API, what's the first thing? Encryption, yes. HTTPS, of course. I don't know who said it. Thanks for the heads up. Essentially, HTTPS is one of the most crucial things. There's plenty of information about HTTPS out there. I'm not going to spend too much time on it. I'm going to stress that HTTPS is really, really, really important. Everything we're going to talk about next kind of builds up on top of that. So if you don't have HTTPS, maybe it's not vulnerable for all kinds of attacks, but essentially there's always one huge weak spot on the network traffic that will compromise all security that you're building. A few guidelines for APIs. First of all, there's no excuse to not use HTTPS. Second of all, you should know that APIs are often accessed directly. So you have an XHR object that sends a request to an endpoint. There's no need in general to support a redirect from HTTP. It's a potential security hole, and if your API runs on a domain that hosts nothing else, nothing that should be accessed by typing a URL in the browser, then there's no actual need to support HTTP. That's one thing that you can already take away from this and can disable if you don't need it. And second, what you should do is you should enable strict transport security on your API endpoint as well, because HSTS, or HTTP strict transport security, will tell the browser that it should always use HTTPS when connecting to your domain, to that domain. And essentially what you tell, or what you avoid then, is network attacks that still try to downgrade to HTTP and become a man in the middle. They will no longer work when you have HSTS enabled. So that's pitfall well, sorry, this is an example of how to configure HSTS. It's essentially a response header with a max age, and the max age tells the browser for the next number of seconds, don't send me HTTP anymore, always use HTTPS, regardless of what you see, things should be done. This is for a year, by the way, so in the next year, no HTTP anymore. Brings me to the first security pitfall, the warming up, so to say. Essentially, provide HTTPS, force the use of HTTPS, either by not offering HTTP and by enabling strict transport security. All right. Let's move on to the next one. Next one is going to take us into the application layer. It's going to talk about the actual application. This is an example from a month ago or 2 months ago, somewhere around that. Maybe you've heard about it. T-Mobile had a nasty vulnerability. Anyone with a phone number could access the account details associated with that number. The problem here is that T-Mobile uses phone numbers. Well, there are two problems. First of all, it uses phone numbers to refer to an account, and phone numbers are public information. By itself, that's not a problem. But the underlying problem is that they forgot to enforce the proper authorization on those calls. So they forgot to check, hey, is the guy asking access to this account information actually the owner of that account? Or is it just someone else who is sitting out there? And this is what we know as the use of insecure direct object references. This has been in the OWASP top 10 for ages. It's still in a new one, but it's wrapped up with another issue. And it's still a problem that we see a lot in modern applications such as this T-Mobile example. And actually, I'm afraid that it's going to get a lot worse, because now everybody is building REST APIs. And REST APIs use IDs by default. Every API has endpoints that take an ID, a task ID or whatever, as an example here. And that everything works fine in your first example, your proof of concept API, and you start building on top of that. And of course, in the tutorial, nobody cares about authentication, because it's a tutorial, it's a proof of concept. You're learning how to do something. Then you start building on top of that. You add authentication, you add authentication checks, and everything is fine. You need to be authenticated to access an endpoint. And what you may forget is a simple check if the user is actually the owner of the task, in this case, before returning the object. And that's something that's often forgotten. And that can become even more problematic if you have functions to make state-changing operations, such as deleting something or modifying something. These functions also require explicit access control. And this is something that's often skipped or missed in many APIs. By the way, I also have the content on the slides, so you can refer to them later if you want to. But most of the things that are on here I already covered during my presentation earlier. So the only proper mitigation here is implementing access control checks. The fact that these direct object references are insecure is because there's missing authorization there. Complementary to that, you can, of course, start to use non-predictable identifiers, but that's not always necessary, and that by itself is not enough as a countermeasure. So that's something definitely to keep in mind. So again, a security pitfall to wrap this one up, the fact that you have missing authorization on these calls to your API is definitely a problem in many, many scenarios. All right. But before you can make a decision whether something is allowed or not, whether the call is authorized, you need some information about who's making the call. So you need session information. And session information used to be something server-side. So back in the day, you all remember we had an application that stores session information on the server. In an API world, people don't like to see this because this means that you have to keep state on the server. It means that you have to decide, if you have multiple servers, which server is going to handle which request. And as a solution, people have thought about, hey, what if we move our session information to the client? Then things become a hell of a lot easier, right? Well, it depends. Sure, it's going to be easier because you don't have to decide which call goes to which server, and you can spin up additional servers and everything keeps working. Now you have a stateless API, which is awesome. But the security properties of what we're doing actually changed quite a bit. Let me give you an example of what I mean here. So first of all, if you have a server-side session object, the data in that object is implicitly trusted. It sits on the server. It's trusted data. Sounds logical, right? The only thing that you send to the client is an identifier. And that identifier remains vulnerable. Client-side sessions are completely different. Now you store actual data on the client, and you trust that data when it comes back. But data on the client should be verified before you use it. And that small change on a picture, just move one object from one place to another, has a big impact for security. That means that client-side data needs at least one and probably two additional security properties. First of all, you need to ensure the integrity of the data you get back. You need to make sure that the client did not tamper with the session data before you start using it. Because if you have a flag in there to allow administrator access, and you simply use that to decide whether that's something that's allowed or not, well, now it comes from the client, so it can be tampered with. That's integrity checking. The second one is confidentiality. If you store sensitive information in the session object, for example, if you're building an e-health application and you store some patient information in the session while the user is working, if that sits on the client, that may be exposed to some users you don't want to. That may be stored on the device, and someone with control over the device can extract that information. So in that case, you might want to employ confidentiality with encryption as well. So client-side session data, even though it looks very similar, and even though in your applications you don't need to change that much code to enable that, it's actually something entirely different and something you need to take into account. One way of doing that is with JSON Web Token. Who here does not know what a JSON Web Token is? Wow, awesome. That's the first time that ever happened, by the way. Just in case. No, so it's essentially basics for encoded data. That's one thing you should know. By default use is also always with a signature. So essentially, the data is protected against tampering. If the client changes this and he cannot generate a valid signature, the server will detect that something is wrong. Well, the server should detect that something is wrong. So in practice, JOT tokens, they're used for all kinds of things. The spec is fairly open in what they can be used for, and they are used to represent claims securely. So essentially, they prevent tampering by default. They also support encryption if you want to. So by default, the token is signed, the server signs it and verifies it when it comes back, and then it trusts the contents of that token. Unfortunately, many libraries also offer a decode function. And a decode function simply decodes the data from base64 to a JSON object without verifying the integrity. And as a result, it often happens that a developer uses decoding functions instead of verification functions. And because of that, you don't verify the integrity of the object, and you still have a vulnerable API. Two code examples to illustrate what I mean. The top one is how to verify a signature using one of the popular JOT libraries for Java. And the bottom one simply decodes the value. This one verifies the signature. You can also see it's a lot more complicated than this one. So you're going to find people that use the decode function instead of the verify function. On top of that, the fact that it's named decode may result in potential or accidental abuse or misuse. So, well, I would have liked it better if they called it insecure decode or whatever, just to give you a hint as a developer, like, hey man, what are you doing? There are valid use cases to use these functions, but they often get misused, resulting in a security pitfall where you have non-tamper proof tokens. By the way, getting this wrong is something you will not notice during any of your regular testing. Everything works as expected. It only occurs when somebody actually goes in the token, decodes it, modifies it, re-encodes it, and submits it again. And when that happens, then bad things happen. All right, let's go a little bit deeper into the JSON Web Token rabbit hole. Actually, many people use JOTs, JSON Web Tokens, JOT tokens, but not too many people know that there are two ways to generate a signature. There's one way with a shared secret and one way with a public and private. Let me show you what this means in practice. Then we're going to talk about what this means for security. So the first is the most common setup. Essentially, that's the one I showed you in the screenshot from jot.io as well. Essentially, you have payload data, you pass it through your library, and it's going to sign this with a shared secret. And out comes this JOT token, which is signed, and nobody can mess with that unless without detection. So whenever that JOT token comes back, the server passes it to the library again. Library is going to use the same shared secret here to get the data out of it again. And at this moment, you can use the data, and you know that it has not been tampered with. This works perfectly well within a single application. However, if you want to use this in a more complex scenario, for example, OpenID Connect uses JOT tokens. If you use OpenID Connect, for example, login with Google is underlying that mechanism is OpenID Connect. What's going to happen is Google is going to give you a JOT token with your identity information. And the application is going to use that to couple that to an account and to log you in. Google is not going to give you their secret or the application, the secret that they use to sign it. So the application cannot verify the token with this mechanism. And if it can, then it can also generate valid tokens in name of Google. So that's definitely not a recommended scenario, even though some people actually use it like that. Some people actually share this secret with third parties, which is not good. If you need that, you need to use the second mechanism, which is exactly how it's used in OpenID Connect, by the way. So it looks the same, but instead of signing with a shared secret, you sign with a private key, and out comes this token. And everyone who wants to use this token can verify the signature with a public key, and you get the payload data out. So essentially what this means here is that you can verify that this, I'll use this screen as well, just to be fair. So you can verify that Google actually signed this JOT token, and you can trust the information that's in there for use in your own application. This is something that's really, really, really important to realize, and that people often get wrong, or even get the wrong security advice about sharing this key with other applications. So, like I said, I cover the same in the slides here. So we covered this already. Should never share this key with other applications, but also don't share it with your client-side front end. If your Angular application or whatever needs to rely on the data in the JOT token and you want to verify the integrity, then you can use, again, the public key, private key setup and verify it with the public key on the client as well. The issuer is the only one that should use the shared secret for generating secrets. And this does not mean that the setup with the shared key is a bad one. It works perfectly well in an isolated service. In a single application, that's a recommended way of using these things, but not in a more complicated setup where you have distributed, distributed use of that token. All right. Moving along quite nicely here. The next topic remains in the same area. So essentially what we have now is we have our API, we have our browser, and we're going to send some kind of identity information, some kind of session object maybe, some kind of claim about who we are. What is really important is that, of course, this information is actually checked somewhere. That's the first thing, but also that you check it throughout your entire system. So what you often see is that there's not one API, but there's a lot of different services that each have their own responsibility, either whether they are your own or someone else's, doesn't really matter. Essentially, there's a lot of interaction there. And one of the really important things to do is that you spread that identity information throughout that system. That every service has the right information to make certain calls. And this is something that, again, is not often done, even if you don't have different services, but you have one big monolithic backend. The authorization information is often only checked at the entry point, but not throughout the application. And this is, if you do this correctly, then you actually get everything you need to make proper authorization decisions. Each of these APIs now has identity information about the user. They can decide whether something is allowed or not. And what you store in there, that kind of depends on the application that you're building. If you do this right, you have proper access control, you have proper audit logs, and every service can make their own decisions about what is allowed and what is not. And I mentioned this before, OpenID Connect actually supports a lot of these deployments, and this is one example of a JOT token from OpenID Connect. And as you can see, it contains information about the user, it contains who issued it, the subject about who the token is, it contains expiration dates and stuff like that, but also identity information, the roles that are assigned to the user, and this ACR attribute is actually the strength of the authentication used when the user logged in. So you can use that to decide whether really sensitive operations should only be accessed if two-factor authentication has been used, and that is defined in this attribute. So this gives you a lot of possibilities to propagate that information and to use it properly to make security decisions in your APIs. All right, let's talk about, I have a question for you again. Just to make sure that you stay awake during these last 2 talks. I know it's been a heavy day, maybe even 2 days if you were here yesterday. So there's 2 ways of transporting this session information. One is using cookies. Who here is using cookies to access their APIs? Again, no one. Really? Who's using APIs? Maybe I forgot about that one. Okay, not too many people actually, so that might have explained a few things. Who here is using the authorization header to transport secure authorization information? Many people. Are you using absolutely no cookies at all? Not even for your login service or something? Yeah, that's often actually a combined setup. So this one works really well in a lot of situations. Applications like Angular applications can easily attach that to outgoing requests, so that's often used. But then in practice, cookies work quite well with the browsers and with web things. So cookies are often used to store more long-term information to access single sign-on services, things like that. So they actually are used in combination, and they both have very different security properties. And I want to go over each of them to make sure that you fully understand what they're about and how they impact the security of your application. To be honest, cookies are a mess. If you talk about cookies and cookie security, which I do regularly in my trainings, you talk about cookie flags, HTTP only secure, you talk about cookie prefixes, which is fairly new and changes the name of the cookie to enforce more security properties. It's a mess. The fact is, they actually work more or less quite well with web solutions. They are attached to outgoing requests from the browser. So even if you load an image with an image tag, the request that goes out will carry cookies. And if you open things like a WebSocket, the request that goes out will carry cookies. So cookies are fairly compatible with the web. Cookies require a lot of effort to secure, like I said, the security flags, prefixes, and they also suffer from something called cross-site request forgery, which I will talk a bit about in the next topic. Essentially, if you have a non-web application and you want to secure cookies the right way, you want to take these security properties into account, it's a nightmare to implement support for cookies. And as a result of that, many people here are not using cookies to access their APIs because it's messy. And the authorization header looks a lot cleaner. And essentially, the authorization header is a custom header where you add whatever you want as the value of the header, and you send that to the server. You can attach that easily from JavaScript, and it looks very clean, very nice. Yet, it's not present when the DOM triggers a request. If you have an image tag that loads an image, if you have a script tag that loads a script, there will be no authorization header. At least your application will not be able to add an authorization header to those requests. So if you want to enforce access control on script files, on images, things like that, you will need to use cookies anyway, because there's essentially not really another way to make sure that that works, at least with the authorization header. And if you have things like WebSockets and cores, it becomes a bit more complex because this is a custom header and these requests are not under your control. So there's not really anything you can do to add these headers there. And securing these mechanisms seems simple, like, yeah, it's a token and you store it and you attach it to the header. And it's actually more difficult than you might think because there's new security things, new things that many people overlook and cause problems. So one example is the fact that you need to store it somewhere in the application. With cookies, you have the cookie store. You can mark them as HTTP only, and they're fairly inaccessible. With the header, it's often stored in local storage. And as a result, every page within that origin can read that token and abuse it if it wants to. So it requires you to have very strict client isolation. And the second problem is, if you attach it to outgoing requests, chances are that you are attaching it to too many requests. And I have a code example in the next slide for this. So one example is, for example, this is an example from Angular. In Angular, you can define an interceptor that attaches tokens to outgoing requests. So it's essentially, the code here is very simple. It intercepts a request, it looks up the token in local storage, and it adds it to the outgoing request. Looks good, right? Very simple, very clean. There's one big problem with this. This works perfectly fine as long as you access your own API. The moment you send a request to a third-party API, this thing is going to intercept it. It's going to be like, oh, I have a token. I'm going to attach it to the outgoing header. And you're sending your session token, your access token, your whatever, just to a third-party backend, which can do whatever it wants with this. And this code is actually really, really, really common because everybody who looks for this finds these examples. And honestly, they get it wrong. If you use a proper library for this, for example, the JOT library for Angular, they have a whitelist of domains. You explicitly need to list which domains should have or should receive your access token. But the default solutions presented like this do not do this. As a result, you have changed the transport mechanism from cookies to the authorization header because it seemed a lot cleaner, but in practice, you have to deal with a lot of stuff yourself again. So JOT tokens or the authorization header don't make it easier, they make it different, but not necessarily easier. Maybe a bit more standardized, but there's still security problems that occur there. So I promised to talk a bit about cross-site request forgery. First, again, who knows what cross-site request forgery is? All right. Who doesn't know what it is? It's okay. All right. I'm going to walk you through a scenario. I'm not going to go into too much detail here. I'm going to explain to you what the attack is about and then how it relates to an API. I'm going to stand here because it's an image and I need to point out what's happening there. So essentially, the setup is you have a browser of the victim, let's say your browser, for example, and you have a legitimate website. You log in to the website, you get a page, and you get a cookie in return. That's how cookie-based sessions work. Imagine that that's your login service or whatever. Whenever you send a request to that domain again, the cookie is going to be there by the browser. Now, CSRF happens when another website tries to do the same thing. So you get another website in your browser. This is something you do every time you use a browser, you use different contexts. This one is going to send a request to that backend, which is, again, legitimate browser behavior. But the browser is going to attach that cookie because the browser is very helpful with cookies. So whenever a request goes to that domain, it's going to attach a cookie here. Of course, if this server doesn't know that this request comes from somewhere else, then he's going to execute this in your name without even thinking about it twice. And that's cross-site request forgery. It's cross-site because this context sends a request there, and that's a forged request trying to perform operations in your name. If I explain it like this, it seems like a silly problem. Like, come on, who doesn't check these things? How difficult can it? Well, actually, it's more difficult than you might think. And there's more products vulnerable to this than you might think either. Everybody has a home router. Home routers have web interfaces. Well, except the one from Apple, but all the other ones have web interfaces. And of course, a web interface accepts requests. So an attacker can send a forged request with HTTP authentication admin here, very important, to your router to change, for example, DNS settings. And that's exactly what malware does. Or malicious websites try to change your DNS settings. And if it works, they control your router. They can send your traffic anywhere they want, which is, of course, the setup for more complicated attacks. And this happened in South America against banks, for example. So they launched an attack, wide-scale attack against popular online banking systems by redirecting DNS traffic from routers with CSRF. So cross-site request forgery, I'm going to the API part. It exists because the browser simply attaches the cookies to outgoing requests without thinking about it. And the fact is that many backends don't check where the request is coming from. Hence, they are not able to protect against cross-site request forgery. In an API context, it depends whether this is a problem or not. If you're not using cookies at all, you're good. CSRF is not an issue. The authorization header, by definition, cannot cause CSRF attacks. But many people still use cookies for authentication and services or endpoints. If you have a single sign-on service, the cookie maintains a session there, and you get, for example, access tokens from there. So this thing starts mattering if you have any of these things that accept requests from DOM elements. So essentially, to defend against CSRF, the traditional way is using form tokens. Surprisingly, in an API, form tokens don't work so well. So you'll have to use something else there. There's two common techniques or two things that matter in an API for CSRF. The first one, if you have actually a legitimate API, you can use something known as a transparent token. And let me show you how it works. So this is the setup scenario again for CSRF. And instead of giving you one cookie, the service is going to give you two cookies, one regular cookie and one with a CSRF token. And the application is going to copy that CSRF token into a header. This is a piece of JavaScript that copies this cookie value, which is not HTTP only, by the way, into this header and sends it to the server. That's the legitimate scenario. If the attacker comes along, he tries to make the request to the backend. The browser will attach the cookies, but because of the browser security policy, this context cannot read that cookie. So it cannot attach this header to the request, so the server will know that this is not a legitimate request. That's phase one. Essentially, this is how you protect, for example, a backend in an Angular application scenario, because Angular does this by default. By default, it looks for this cookie, and it attaches this, automatically attaches it to outgoing requests in that header. So if you do that, the server can detect whether these are present, compare that cookie to that header. If they are, it's a legitimate request. Otherwise, it's coming from God knows where. That's a traditional CSRF case that actually still matters for some APIs. Because the browser does not allow you to read cookies from other domains. Does that answer your question? All right. Yes, absolutely. Well, there are also backend libraries that do that automatically, but yes, you will need to check this on the backend, absolutely. Now it becomes really tricky if you bring CORS into the mix. CORS stands for cross-origin resource sharing, and essentially CORS is the mechanism that enables your browser to make XHR calls across origins. So a long time ago, back when you had Firefox 3, I think, you could only make XHR calls to your own domain, your own origin. Anything that goes somewhere else is denied by default. Well, that changed when they introduced CORS, cross-origin resource sharing, and they actually added a lot of security on top of XHR to make sure that the server expects a request and handles it gracefully without exposing legacy servers to attack. So in an API, a lot of requests, well, all requests are XHR requests. So if you go cross-origin, then the browser will automatically attach an origin header to the request, so the server knows where you're coming from. The problem is if it happens within, or if your API accepts requests that can come from a form, for example, then this will not work, and the origin header will not always be there. So the case is twofold. If your API supports traditional requests, meaning anything that can come from a form or an image tag using traditional content types and no special headers, then you need CSRF protection. If your API only supports non-traditional requests, for example, if you have a JSON API and only accept application/JSON as a content type and not something else, then the browser will automatically attach this origin header to the request. And that means that you can automatically check the origin header for its presence, and that if you don't submit the proper headers, then you will not expose information to third-party contexts either. And there's two common ways you can force this behavior to happen. I gave away one. Well, there's actually two. So one, you can simply add a custom header. You can choose whatever you want, and by adding that header, you can make sure that nobody else can send a request without the origin header be present. Because a form, if you submit a form across origins, it will never be able to send you custom headers. The attacker has to use XHR, and when the attacker uses XHR, the origin header will be there, and the server will know that something is going on. The second type is second way is, for example, forcing the content type. You have to make sure that your API does not accept anything else. Many APIs also, for example, accept text/plain and simply parse it as JSON, and then you're still in trouble. So definitely keep track of what you're doing there. Brings me to the second to last pitfall: don't underestimate CSRF. If you don't use cookies for your API, then that part is covered, but you still need to check your single sign-on service or whatever where you do use cookies to make sure that they don't leak tokens and things like that. I have one more to cover. I'm going to start with a question again. Should your API accept this as input? Yes. Who says yes? All right. Who says no? 4. Great. Who has no idea? It depends. Sometimes yes, sometimes no. And as you can guess, the last part is about input validation, checking what you receive as input. And to be honest, some people would have started with this as the most important thing. I don't necessarily agree. So yes, of course, if you expect a number, then this input is bullshit. It should not be accepted. But if you expect a name for the user, then you have no idea whether this is actually valid or not. Names are actually one of the most difficult, one of the very difficult things to validate input-wise, because the worldwide population has crazy names. What's the only solution that you can use against this, or what's the proper solution? Proper solution is to address the actual cause, which is in this case SQL injection. So you have to use parameterized statements, as Matthias mentioned this morning during his talk. So input validation, in a nutshell, input validation is very, very useful, but it's not a good defense if you use only input validation. It's a very good first line of defense. So input validation can weed out the weird things that should have never reached your API. And that's definitely one of the useful things about input validation. So best practices here are only accept content types that you expect and reject everything else. If you expect a number, then verify that you get a number. If you expect a date, verify you get a date, things like that. And these sound silly, again, but you would be surprised how many APIs accept just whatever you send them. But input validation is not the holy grail. It only gets you so far. So don't rely on input validation as a security measure. Use it as a first line of defense to keep the bad guys at least a bit further out the door. But essentially, it's not a very good security solution if you only use that. So bypasses will always exist. There's plenty of research papers showing how to bypass things like cross-site scripting, filters in the browser, stuff like that. And sometimes the API doesn't even care. So we haven't talked about that, but if you, well, because in an API world, cross-site scripting doesn't matter anymore. The API has no idea where the data is going to be used, so it cannot even protect against cross-site scripting. that becomes the part of the client-side application. That's why Angular application and things like that, but that's why they deploy sanitizers to make sure that content injected into the page is actually safe data and not God knows what coming from the API. That actually brings me to the last one. And the last pitfall is over or underestimating input validation. So use it as a primary line of defense. Don't think it's not even useful. It is very useful, but it has its limits and you need to be aware of those. Instead of giving you a full recap of everything I covered, which would, well, it's already an overview presentation, so a recap of an overview is just plain boring. I want to conclude with a small piece of advice, and that's question everything, especially if you're moving towards a new paradigm like an API. Question what you're doing, question everything that you're doing. Essentially, that comes down to, is this different from what we're used to? What's the impact of moving session data to the client? Does that change any security assumptions that we make about that content? And that's going to get you actually quite far. Like I said, when I introduce myself, I'm a trainer in software security. I tell people how to do it, but then it's up to them to actually build more secure applications. So that's one of my send-off messages. Build secure stuff, definitely do that. Follow people that know about security, myself and other speakers, of course, included, and share your experiences. If you build or secure your applications, if you do something to improve the security, you have that experience, share that with your colleagues internally, and if you can, share it outside, on OWASP chapter meetings, on BeNeLux days, on conferences, whatever. Many people need more experience on how to do it, and they get that from you. And that's it for me. Thanks for being here.
Thank you, Philippe.